Okay, so is the screen visible?
Yes.
Okay. So Satya is here, but I want the other students also to respond. So yes. Yeah. Okay. So yeah, so in the last week, we were looking at constrained optimization and in particular the Lagrangian dual. Okay, and just a quick recap. So what we saw was how to write the dual. So we defined something called a dual function. Okay, so which computed the Lagrangian and the infimum of the Lagrangian, and this was a lower bound for our original function that we wanted to minimize. Okay, and so this was a function of lambdas and the mu's, where the Lagrangian was written in this manner: f of x plus summation lambda gix plus summation mu j at jx, where the inequalities took this form. Gix was the inequalities, and they were all less than or equal to 0, and Hgx is the equality constraints. Okay, so this was the Lagrangian, and we wrote the dual function. And the Lagrangian dual problem was to maximize the dual function with respect to the lambdas and mu's. Okay, and so we called this as D star, the Lagrangian dual, and the primal was denoted by P star, and we always had that this was true. D star is less than or equal to P star. Okay, and so we saw some examples. I mean, we saw an interpretation, and then we saw some examples of how the dual could be written. Okay, so a couple of examples, and then we saw that you may always not get a closed form for the dual. Sometimes you might involve the primal variables too. Okay, and then we also saw LPs. So we had learned linear programs in the past, and we saw how to write the dual there. And there was a slightly different approach we took at that point to write the dual, mainly to construct a lower bound. Okay, and we saw that writing the Lagrangian dual also gives us back the same dual that we wrote earlier. So whatever LP duality you've learned here, it actually turns out that it is the Lagrangian dual indeed. Okay, so an exercise for all of you would be to try to write the dual for different forms. Okay, so we saw different forms of LPs, like things like Ax equal to B, or if you didn't have X greater than or equal to 0, and so on. So for all these, check again when you write the Lagrangian dual, what does it give you? And compare it with what you got earlier, with the earlier approach. Okay, and then this is kind of where we stopped in the last class. Okay, so today I just want to start off with one more example. So this is a quadratic program. Okay, and this comes up in many places. Okay, so I thought it's just useful to take one more example here. Okay, so the optimization problem, the objective is half x transpose qx plus c transpose x, and subject to some linear inequalities, ax less than or equal to b. Okay, and so x in Rn, so this is going to be the set capital X. Okay, and the Lagrangian, so let me call the multipliers here as say lambda. So here A is a matrix of size m cross n, so which means that there are m inequalities, and so there are lambda 1, lambda 2, and so on up to lambda m, okay, corresponding to each of these inequalities. Okay, and so yeah, let's start writing the Lagrangian. So the Lagrangian is always a function of x and lambda. So what would the Lagrangian be here? Somebody wants to go ahead, answer. Okay, you don't have to feel shy because Satya is here, but you can just answer anyways.
So one of the applications of this actually is SVM. So we will have exactly the same formulation in a couple of classes. So it's good if you really try to apply yourself here because it will help you there as well.
Half x transpose qx, basically the function.
Yes, half x transpose qx
plus c transpose.
Right.
Plus summation lambda I AI x minus b.
Okay, so let's call these constraints AI transpose X is less than or equal to BI. Okay, and I equals 1 to M. So this would be, yeah.
Lambda I multiplied by AI transpose x minus bi.
Minus BI. Right, so this is I is 1 to M. Okay, so this is the Lagrangian. So one thing is you could write this in short, like this is the exact form. And in another way to write this is lambda transpose AX minus B. Okay, so this is something you can just verify, like when you take this lambda I AI transpose, I mean, in terms of the matrix form, the summation boils down to just taking lambda transpose AX. So this is something you can, manually check the computation. So I'll urge you to do it later. Okay, so this is now the Lagrangian, half X transpose QX plus C transpose X plus this. Okay, so now what we are trying to do is inf of X in Rn. So the dual function which we write as, let me just write it properly. So theta of lambda, that is the dual function. And that is just, you're trying to find the infimum of X with respect to this capital X, which is just Rn. So, and half X transpose QX plus C transpose X plus lambda transpose AX minus lambda transpose B. Okay, so now this is an unconstrained optimization problem. There are no constraints on X, finding the dual function. Okay, so one more assumption I'm going to make here is that Q is positive semi-definite. Okay, so the reason I make that assumption is now this function, the Lagrangian, is going to be a convex function in terms of X. Because if you take the second derivative of this, you are going to be left with Q, and which is positive semi-definite. So let's just start by taking the gradient of this function, because that's what you need to do to find the infimum. So what's the gradient of this? So gradient of this function here, this whole thing with respect to X.
X transpose Q plus C transpose plus
Okay,
lambda
X transpose Q plus C transpose
plus lambda transpose A.
Okay, so I'll just write it in the transpose form. What if you do it this way, what you're going to get is a row vector, because this is 1 cross n and you have, this is correct, right? Yeah, 1 cross n and this is n cross n. So what you'll get is a 1 cross n. So it's a row vector. I'll just write it in terms of column vectors. So this is equal to 0. So what I do is I'll just take the transpose. So that Q is positive semi-definite and the assumption is it's symmetric. So what I'm going to get is Qx plus C plus A transpose lambda is equal to 0. Okay. So this is what, so an X, X which minimizes this this dual, the corresponding X for this dual function, the one that minimizes this function written here, is such that Qx plus C plus A transpose lambda equal to 0. Okay, this is the minimizer for this. Okay, so now.
So why are we not taking the derivative with respect to lambda?
So in terms of the dual function here, so this is a function of lambda itself, the overall dual function. Okay, so the derivative here in terms of the dual function, it's only the inf over the with respect to X. And finally, what you're going to do is you're going to maximize theta of lambda with respect to lambda. Right, so the minimum is only with respect to X. So in terms of this function, lambda is fixed, lambda is given. Okay. Okay, so yeah, so now this is the X that we have got, which is optimal for this problem. Okay, so now what we need to do is, if we need to find, we need to write the dual function in terms of this X, okay, what we've got as the optimum. Okay, so we need to transform this to a function involving only the lambdas, if possible. Okay, so let's just try to do that. So to do this, what we are again going to do is we need to make some substitution here. Okay, so for these values of x. So one way is I'm just going to write this objective slightly differently. The theta of lambda ultimately, so I'll just call this x star, okay, because x star is the one which minimizes this. So what I need to write is half x transpose q x star. So this is the optimum x star plus c transpose x star plus lambda transpose a x star minus lambda transpose b. Okay. So now one thing I'm going to do here, so this is just the objective, and I'm just going to add a half x star transpose q x star. And so I will just subtract 1 half x star transpose q x star. So what will this give me? So I can group these two together. So what will it give me?
X transpose Q X star.
Yes, so x star transpose q x star plus, I'll just write this as x star transpose c, yes, plus maybe x star transpose a transpose lambda minus lambda transpose b. Okay, so I mean I just wrote it in this way for a particular reason. Okay, so here what I can do now is I can just take out, you know, okay, I think again I messed up a little bit, but no. Okay, so I think it's fine. So I'm just trying to simplify the objective a little more. So what I'm going to get is x star.
So I have a question here. So if you
Yes,
are doing this X star, like you're taking the transpose essentially. That's what you did for C transpose X star, you took a transpose.
yes.
So is that always permissible?
So in this case, what happens is this is, so what you'll get with C transpose X star is just one number, right? So this is just going to give you summation Ci. So let me call it Cj. So j is 1 to n because there are n variables, and Cj xj star. Okay, so this I can also write it as xj star Cj. Right? So this is the same thing because this is going to give you finally the C transpose x star as a single number. It's a scalar value. I can take the transpose. You're going to get the same thing. But yeah, in general, you cannot do that. It's not the same.
Okay.
Right? Okay, so that's a good
And the
point.
half X star transpose Q X star is minus half.
There's a minus half. So let me just write this part once. So, okay, here you're saying, right? There's a half. Okay, good, thanks. So there's a one more half here, minus half x star transpose q x star. Okay, so what I'm going to do is I'm just going to club these together. So what this is going to be is just x star transpose. I mean, I can take the x star as common. So qx star plus c plus a transpose lambda minus lambda transpose b and minus half x star transpose qx star. Okay, and now we know that the x star is such that it has to satisfy this. At the optimum x star, which minimizes the dual function, you need to have this relation is true. So in
There
turn,
Q instead of Q transpose will come
which
in
one?
the above box. Yeah.
Here?
The yes,
Yes.
yes box.
So the assumption is Q is positive semi-definite and it's symmetric. So Q is also symmetric. So that's where you can, Q transpose is equal to Q. Okay, so yeah. So then what is going to happen is this part is 0. Qx star plus C plus A transpose lambda is 0. So this term vanishes. And what you're left with is minus lambda transpose B minus half x star transpose Qx star. Okay, and so this is the function that you want to maximize. Okay, so theta of lambda is actually this. So theta of lambda is exactly this value. So what you've written here is theta of lambda using the optimum x star. And so this is just minus lambda transpose B minus half x star transpose Q x star. Okay, and now the dual is to maximize theta of lambda subject to lambdas taking a value greater than or equal to 0. So here what we are going to get is maximize minus lambda transpose B minus half x star transpose q x star, okay, subject to lambdas greater than or equal to 0. That's the function. Now another thing is this x star, it's not just any x star, it's a very special x star which has to satisfy this. Otherwise it will not correspond to the dual function. So you also need to write q x star plus c plus a transpose lambda. These are also constraints for the problem. Okay, and now x star is also variable. Okay, so here x, so let me just write it as x itself. Okay, so that now it is a fixed value. I mean, it's a variable to the problem. So this optimization problem is over x as well as lambda. Okay, so if this x is unique, yeah, you have just one value, but otherwise, the x is also a variable to this problem because you cannot completely eliminate it here from this expression. Okay, so this is another example of the case in QPs where your dual will involve both x and lambdas. Okay, but
is there a range for x? I mean, shouldn't it be x belonging to x or something?
So here the x is just Rn, so that's fine. So yeah, x is in Rn, that's also there. Okay, but there are no other constraints on x other than this part. Right?
Yeah. Okay.
Okay. Yeah. So yeah, these are some of the subtleties you need to take into account when you write the dual function. So if you had some other constraints, okay, in capital X, like we did earlier, things like x is greater than or equal to 0 or something, and suppose in the form you got, you were not able to simplify it further, then you would also need to include those constraints. But in this case, it's just x in Rn, so it's just fine. We did an unconstrained optimization, and one thing is this was indeed the optimum. The optimum x star. I mean, if you got an x star such that this was satisfied, that would indeed minimize this problem because this was a gradient, and the second derivative of this with respect to q, I mean, second derivative of this function with respect to x is just q, and that is positive semi-definite. So this is guaranteed to minimize the dual function. Okay.
Can we look at the case where q is chosen as identity?
Yeah. So so that is a special case where some nice things happen. Okay. So in fact, I think that's what will come for SVMs as well. So when x is, let me just maybe write it on a new page. So suppose q is identity. So in this step, what you would have got, right? Everything remains the same, but here you substitute like this is identity. So what you're going to get is x star plus c plus a transpose lambda that is equal to 0. Okay, so I said, yeah, this point, when you try to take the minimum, when you try to construct the dual function, what you're going to get is x star plus c plus a transpose lambda is 0. Okay, so now this means that there is a closed form expression for x star. So x star is just minus c minus a transpose lambda. Okay, so this is, so you have a unique solution here. Okay, now when you try to write the dual function, so the dual function, let's just write it again. So theta of lambda is half x transpose qx plus c transpose x plus what was the other thing we got? Plus lambda transpose ax minus b, right? So lambda transpose ax minus b. And the x you need to substitute is, so x is equal to minus c minus a transpose lambda. Okay, so now we have to just substitute it back here. So we have a closed form expression for the x. Now if we substitute back here, what we are going to get is, let's just write the overall expression. So we are going to get minus c minus a transpose lambda transpose q minus C
Q
minus
is identity.
Q is identity, right? Thanks. So here Q goes off, so it's just this. Okay, so minus C minus A transpose lambda. I'm just writing the overall thing, so and we can simplify it. So C transpose minus C minus A transpose lambda. Okay, plus lambda transpose A times minus C minus A transpose lambda. Okay, and minus lambda transpose B. Okay, so
it may be easier to just start off from the point where you had simplified already to an extent, right? So this one,
right?
yeah.
Okay, let's just write it that way.
Lambda transpose P minus half X transpose X.
So the dual function, so the overall dual is what we'll write. So set lambda is greater than or equal to 0. So this is what? Maximize minus lambda transpose B minus half X transpose X, right?
Yeah.
Yeah, half X transpose X. And
subject to lambda greater than 0.
Yeah. Lambda greater than or equal to 0, and X we have a closed form now. So X is minus C minus A transpose lambda. Okay. So this is directly, if you substitute the value we got from the QP, this is what you're going to get. But, since you have this closed form expression for X, you can possibly try to eliminate the value of X from the objective completely. Okay. So let's just do that. So it's just maximize minus lambda transpose B minus half times so there is a minus, so this is minus of C plus A transpose lambda. And there's a X transpose X. So the minus and minus go off. So I'll just write it as C plus A transpose lambda transpose C plus A transpose lambda. Okay. So this is lambda greater than or equal to 0. So now you see that there is no X in the objective. Okay, so you can completely, eliminate it. So this in turn becomes minus half. So if I expand this, I will get what? C transpose C.
I think that's not necessary. I think
That's fine.
that's fine.
You can simplify it further, right? Like
yeah. So this is precisely the SVM thing. So that's why I wanted you to just do it once for.
Okay.
So we will see a special case in ML.
Yeah, so this is what shows up in SVM, okay? Yeah, so the particular details, I guess you will do it in the ML class, right?
That's right.
Okay, so are there any questions till this point? Has it been clear so far? Anything you can type, whether it's clear or not clear? Yes, no? Clear? Clear? Okay. So what about the others? Siddharth, Bhavna, yes. Harsimran? Lakshmi, clear? Okay. Yes, okay. Good. So so hopefully this will give you a good idea of, writing the dual, the examples that we've taken. So one thing, let's just now try to analyze the dual function a little more. Okay, so one result is that this dual function, this theta of lambda mu, it's always going to be a concave function in terms of lambda and mu. Okay, so so this is an important result in the sense that it leads to the dual being a convex optimization problem. Okay, so we'll just see an intuition for why this is the case. So the theta of lambda mu, the dual function, is always a function of the lambda and the mu. Okay, so now, and it's of this form, right? Inf over the x in your domain, and f of x plus this function. So in particular, this is a linear, or it's an affine function in lambda and mu. Okay, so this particular thing without the inf, this fx plus summation lambda gix plus summation mu j. This is an affine function in the lambdas and mu's. Okay, so let's just take one a small, just to give you an illustration of what the inf would be.
So this is not just F. I mean, affine is okay, but it's also convex as well as simultaneously concave.
Yes, yes, it's convex as well as concave.
Because linear is in the boundary of that condition.
Yes, it's the only function which is convex as well as concave. This is only class of functions which are both convex and concave. Right? Yeah. So so here what we are doing is we are taking an infimum over several affine functions. Okay, and it turns out that that is a concave function. Okay, so just to get a sense of what we are doing here, I'll just take one example where there's a single constraint. So there's just one lambda. So what I'm going to do here is I'm just going to try to plot the dual function. Okay, so lambda goes on the x-axis and theta of lambda, I don't know, theta of lambda. So the Lagrange, I mean, maybe this function. So L of x lambda, where the x I will plot different values of x and for different values of x.
May I make a suggestion? Perhaps you can just take infimum of several concave functions and show that that also is concave, right?
Yeah,
No,
that's
that will,
true. Yeah. So
just a figure.
So I just want them to also see that, in terms of this x, so what actually it means when we are varying the x, right? So what we're going to get is a different set of functions. Right?
Okay. Yeah.
So more generally, that's true. If you take concave functions, the inf is going to be a concave function as well. Okay, so so I'm just going to leave this the part corresponding to x as a blank. Okay, so what I'm going to do is I'm going to take maybe some 4 values, say x1, x2, x3, x4, some 4 fixed values. Okay, and this function f of x plus summation lambda gi plus summation mu j hj for a particular value of x1, I mean, as a function of lambda. So this is one constraint. So fx plus lambda gx. Okay, so that is what I'm going to plot here. And for a particular value of x1, what it's going to look like is maybe something like this. Okay, so this is L of x1 and lambda. So as a function of lambda, it's going to be a line and it's varying in this manner. Okay, now if I take some other, say x2, so what you're going to get is maybe something like this. Okay, and for x3, maybe you'll get something like this, and so on. Okay, and x4, maybe something like this. Okay, so this is x2, x3, and x4. So corresponding, so this is L of x4 lambda, L of x2 lambda, and so this is L of x3 lambda. Okay, so you get different lines corresponding to each of the x's, and like that you have many lines corresponding to each x in the domain capital X, you will get a different line. Okay, so what we are saying when we compute the dual function is the inf over all these lines. The function, it's also a function of lambda. So theta of lambda is actually the inf of all these lines, the minimum, the piecewise minimum of all these lines. So what that's going to be is in this range. So first, this line is the one which will give the minimum value. So till here, it's going to be this line. So it's going to correspond to x4. Now in this range, it's going to correspond to x2. It's going to correspond to L of x2. So you'll get this line. Okay. And in this range now, this Lx3 lambda, that's going to give the minimum over all these Lagrangian lines. Okay. So that here it's going to be something like this. So you see the general form here. So this is a concave function. Okay, the one that I've marked in red. So this is the concave. It is a concave function. Of course, we are plotting it against lambda, so concave in lambda, and this is exactly the dual function. Okay, so theta of lambda. So you see that the dual function is always a concave in lambda. Okay, you can prove this more generally using some of the concepts we learned about convexity and proving things about operations that preserve convexity or concavity. Okay, so that is something like by the definition of concavity, of concave functions, you can actually prove this. But the idea is just this, when you can see it pictorially, maybe it makes more sense. So this is a concave function. And when you're trying to maximize this function, it's a maximization of a concave function and subject to lambda greater than or equal to 0. So this set is convex. So this is a convex set. And what you're trying to maximize is a concave function. Maximize a concave function. Okay, so this is actually a convex optimization problem. Okay, so a convex optimization problem is either you try to minimize a convex function, right? Or you try to maximize a concave function. Okay, so if you try to write it as a minimization form, you're just going to get minus min of minus theta of lambda subject to lambda greater than or equal to 0. And this is a convex function. Minus theta is a convex function and over a convex set. So this is going to always be a convex optimization problem. Okay, so that is an interesting fact about the dual convex optimization problem. So irrespective of what the primal is going to be, so it doesn't matter what the f, what the g, what the h is going to be. Okay, the original problem can be anything. It can be a non-convex problem as well. But ultimately, the dual that you write is going to be always a convex optimization problem. Okay. Now, why is it useful if it's a convex optimization problem? The reason is that we have seen when we wrote the KKT conditions. So if you somehow are able to find a KKT point for a convex optimization problem, then you're guaranteed that is going to be the true optimum. Okay, so the KKT conditions, they become sufficient for convex optimization problems, and that's why this is a nice thing to have. Okay, so one thing to remember is still, convex optimization problem doesn't mean that it's always going to be easy. Okay, so this is something we saw when we talked of convex problems in the initial part, and that is something that you should remember. But for many classes of convex optimization problems, there are good theories that have been developed. I mean, it is sometimes easy to find KKT conditions for some classes, but in general, it's not always true. Okay, so so this fact is something that gets made use of, like for some classes, the fact that convex optimization can be easy, that gets used a lot in various domains, and SVM is one such example. Okay, where that will be true. Okay.
So I have a question here. So
yes.
you got infimum here because it was over the primal was having that form. So if the primal has having different form, this will be supremum. So then what will happen?
So if the primal, you mean if it's a max of, you're saying if it's a max of f of x, is it?
Yes, yeah. So if you take max and then you try to take its dual, then you will get supremum.
So one thing you can do is, if you have max of f of x, you could convert it to a minimization problem, and then you could do the same steps, right? In the same manner, like negative of min of this.
Okay.
Right. So this procedure that's been there, that what we have developed, that we take it as, it's a more general thing. We take it as the given primal is in the minimization form. Okay, but you can convert any of these maximization problems into a minimization form. So it won't affect these results.
Okay.
Yeah. Okay, so so far has it been okay? Are there any questions?
No questions, ma'am.
Questions? Okay. Fine. Yes.
Ma'am, in the dual, every point that we get from when we take the infimum over x, then we convert it into a function of lambda. Every
Yes.
point there is a lower bound, right? For the primal problem.
So every point here in the dual, this function, right, theta of lambda mu, all of these are lower bounds.
Yes, ma'am. Is that the case? I was just asking.
Yes, this will be always true. So theta of so one thing you will see is like from this figure, if you want to see it pictorially, so actually in each of these lines you take, the intercept is actually f of x, right? So because the functions, all these functions are of this form, f of x plus lambda g of x, right? And so the intercept is exactly this f of x, okay, for each of these lines. So all these intercepts, so this is for corresponding to x3, then you have x1, x2, and x4. Okay, so yeah, so this is actually in some sense going to be the, yeah, so your question is whether this is always going to be a minimum for that.
Yes, ma'am. When we take the infimum over x and then convert it into a problem where our variable is only lambda, then for every lambda that we can take, everything is a lower bound for the primal problem, right?
Yes.
But then the question arises that what is the like objective of our dual formation? Because we were finding a lower bound. Why weren't we satisfied with the why are we taking the extra pain of then optimizing over lambda also?
So the reason is you want to get the best lower bound. So if you just take, any x over here, it is not, there can still be a gap, right?
Ma'am, but in the linear case only we were like that had a utility because we could prove strong duality and get the equality there. So in a
Yes.
way optimizing gave us some utility, but here optimizing is giving us just a uh, tighter lower bound, but that is also constrained to the amount of information we have. It might not be the tightest, so because tightest will always be something that is infimum or equal to like the.
So you're saying that, you may not, even if you do this in the dual, you get some D star that may not be equal to the primal P star, right?
Yes.
So then you're asking like, what's the utility of, why is the dual useful, right?
Yes,
So
ma'am.
yeah, so that's a valid point. So one thing is, there are classes where these two problems will match. The P star and D star will match. And of course, in those cases, you definitely have a direct use of it. Now, in other cases, what happens is it could be that the primal itself is hard to solve. And the dual is going to give you something like a guarantee. It's the best that you can do. And you have like, it cannot be worse than this value, right? So in that sense, that's some utility of the dual. When you don't know anything about the primal, you don't have any way to solve. One way it tells you is, this is as far as it can go. It cannot go worse than this, something like that. Okay, that's the use of the dual. Now, one thing we have not talked of is many algorithms for constrained optimization. Since they don't have a way to directly tackle the primal, one thing they do is they go into the dual space. They try to get a dual feasible point, and then they have some sense of what is the this, the limit is this, and then after that they try to construct another primal feasible point. And many algorithms in constrained optimization actually make use of the dual. Okay, so we don't have time to go into those kind of algorithms. So those are these primal dual algorithms. Okay, but one thing you will see is that I will also show you an example, like for these convex optimization problems, under some conditions you'll have that the primal and dual values will match. Okay, so in that case, even there, the primal, sometimes you don't know how to solve it like in exact closed form. Maybe you don't know, but with the dual solutions, maybe the dual is easier to solve, and using the dual solutions you can again construct the primal solution, like similar to how you did in LPs. So some variant of that you could do also for convex optimization problems. Okay. And of course, in some problems, you also have some perspective that comes from the dual. Like it's a related problem, and in some cases, maybe those are like well-known problems that you already know to solve. Okay, so it's kind of giving you a mirror image of the primal. So those are some of the uses of the dual. Okay. Siddharth, did I answer your question?
It's clear now.
Okay. Okay.
So
All right.
just to add, like the theory of this algorithms, approximation theory, and many of these things use this dual. So it's just that we don't, I mean, she doesn't have the time, of course, but there is a lot of application in theoretical computer science, like to come up with the NP-hard problems, you may not be able to know how to solve. But using dual, you can get a lot of improvement, in the sense you can get solutions up to certain accuracy and things like that. So it's really very useful, this concept.
Yeah. Yeah, I mean, there is a whole theory, like he said, in approximation algorithms, which makes use of, the entire idea is to construct dual programs and get good guarantees on the original solution, which, is hard. Okay. So some of these, I think even things like vertex cover and, those kind of problems, they have, they go into the dual space to get good approximations. Okay. So not just in the sense of LPs, but even something like a QP, getting a good approximation for a QP, that also can be done with the dual. Okay, so yeah, so this is good. So let's just move on a little bit. I wanted to also talk to you about these concepts about strong duality and when it holds and things like that. So we saw that the dual is always going to be a lower bound, right? The dual, the way we construct it, it's always going to be a lower bound for the primal. So suppose you have a feasible point x and lambda and mu are feasible points for the dual. So by dual feasible, we just mean that lambda has to be greater than or equal to 0, because mu can be unrestricted. It can take either positive or negative values. Okay, so then the result is that f of x for any primal feasible and dual feasible point, this is true. Okay, and okay, so this is just by the construction. So we took the Lagrangian and we saw that this lambda gix is going to be less than or equal to 0 always for any feasible primal point. Okay, and so because of that, this is going to be less than or equal to f of x. And then when you take the inf, when you take the minimum over all x on both sides, you have that this is true. And so that's how you got that, f of x is greater than or equal to theta of lambda mu. And so now you maximize over lambda and mu, you get a better bound. Okay, and we call this P star and this was D star. And this result is actually called weak duality theorem. Okay, it's just the consequence of the way we have defined the dual. Okay, so this is called weak duality. And we also saw this in linear programs. Now the duality gap is P star minus D star. Okay, and weak duality says exactly this. Now we say that strong duality holds when P star is equal to D star. Okay, so strong duality when P star is equal to D star. And this is always not true. Sometimes it happens, sometimes it won't happen, unlike the case of linear programs. Okay, so let's just see this example here. Okay, so this is an example which we had worked out earlier. So the primal takes this form, x1 square plus x2 square, subject to, x1 plus x2 greater than or equal to 4, x1 greater than 0, and x2 greater than or equal to 0. And we had computed the dual as this one-dimensional problem. Okay, so here, one thing was that, in terms of the primal feasible region, what we got was x1 plus x2 greater than or equal to 4. That corresponds to half space. So this half space actually. And the feasible region is everything which was greater than or equal to 0. So basically all of this. Okay. And now the objective that we saw was x1 square plus x2 square that you're trying to minimize. So, use something like this. This is the objective and you were trying to minimize. This is the contour of the objective and you try to minimize it. So a smaller circle means it's a smaller objective. And so finally the optimum is somewhere like you can see that it's going to be something here, okay, which touches this line. So that is as best as you can go to minimize this x1 square plus x2 square. Okay, so you can see that you will want x1 plus x2 equal to 4. Okay, and one thing that we saw here is that the optimum is actually x1 equal to 2 and x2 equal to 2. Okay, and the objective here is 8. So the P star value was 8 here. Okay, and yeah, so now in terms of the dual, this is also something we solved earlier. And what we did was we ignored this constraint, lambda greater than or equal to 0. And then we get that lambda is equal to 4. Okay, so this is the optimum value of lambda. And what was the objective? The best value. So D star was just minus lambda square by 2 plus 4 lambda. So what you got was minus 8 plus 16, and this was also 8. Okay, so here this was a case where the primal and the dual values matched. Okay, so we had strong duality here. But in all generality, this will not happen. And I just wanted to do one example here of the case where primal and dual values need not match. Okay, so this is one such example. So here you can see that this concept of dual. I also want another point I want to illustrate here is that dual, you can write it. It's a more general concept. It's not only for continuous programs. So in this case, you see that this is it's an integer optimization problem, but here also you can write the dual. Okay, so let's just take this example. So here, one thing is it's not a convex optimization problem, okay, because you have these integer constraints. And let's just try to write the dual for this one. So maybe first let's just write the primal objective.
So why, if having integer points makes it non-convex?
Yeah, so because the feasible region, so in terms of the feasible region, you don't have a convex set anymore. So something like this, if in 2 dimensions, if you take that, suppose these are the feasible points, okay, if these are the integer points. Now, if you connect these, this is not, none of these points are going to lie in the feasible space. Okay, so the feasible space is now no longer a convex set. Okay, so that's why it's not a convex optimization problem. Okay.
Yeah.
Right.
Yeah.
Okay, so now for this problem, let's just see. It's a slightly different flavor. So let's just see what the primal optimum is. It's a smaller size problem, so we can just directly compute the optimum. So one thing is you have this constraint x1 plus x2 equal to 3. So, and x is one of these points. Okay, so you can see that this point 0, 0 is not going to satisfy the constraint because 0 plus 0 minus 3, that's not equal to 0. And similarly, this one is not going to satisfy this constraint. So 4 minus 3, that's 1. It's not going to satisfy. So is this going to satisfy 4, 4?
No.
No, right? So this is also not going to satisfy. What about 4, 0?
No.
This is not going to satisfy. And the only values are this 1, 2, and 2, 1. So these are the only 2 points which satisfy this constraint. Now, out of these 2, the objective function, so it's minus 2 for this one, it's minus 2 plus 2, so which gives 0. So the function values are this 0. And for this one, it's minus 4 plus 1, so that is minus 3. Okay, and the minimum is actually going to be this value, this 2, 1. Okay, so this is the optimum point. Okay, so now let's just see what the dual gives. So here the primal optimal P star is minus 3. Now when I take the dual, so I just write the dual. So theta, there's just one constraint. I'll just call this multiplier as mu since it's an equality constraint. So theta of mu is just inf over x in this set x minus 2x1 plus x2 plus mu times x1 plus x2 minus 3. Okay, so you have these points. You can explicitly enumerate this. So what you're going to get is, this theta of mu is min of the following. So it's of course a function of mu. So if you substitute x1 as 0, 0, so now here you have to take all these points. Okay, you cannot ignore any of these because you have to consider all the points in x. So minus 2, so these will give you 0. And so what you're going to be left with is minus 3 mu. If you substitute x as 0, 0, you're going to get this, minus 3 mu. Now if you substitute 0, 4, what happens? What are you going to get? So this one goes off. So here you'll get 4. And here you get mu, 4 plus mu. Okay. Just substituting 0, 4 into this form here. Now, if you substitute 4, 4, what are you going to get?
Minus 4 plus 5 mu.
Minus 4 plus 5 mu. Okay, so this gives 18. Okay.
Minus
Fine.
8 plus mu.
Minus 8 plus mu. So that is if you take 4, 0. Yes. Now the other two.
Zero.
So this constraint will be 0. Now here, 1, 2. So this will give 0. So minus 2 plus 2, so 0. And the last one?
Minus 3 plus nothing.
Yeah, so this also vanishes because this constraint is satisfied. Okay, so you have that, it's a min of all these functions. Okay, so that is the dual function. And let's just see, like looking at this, there are some things we can just directly eliminate. So between 0 and minus 3, of course, minus 3 is always going to be min. So you can eliminate this 0. Okay, so this can be eliminated. And also between mu plus 4 and mu minus 8, right? So mu plus 4 you can always eliminate because mu minus 8 will always be lesser. Okay, so what it's going to give is minus 3 mu. So minus 4 plus 5 mu and minus 8 plus mu and minus 3. Okay, so the dual function is a minimizer. It's a minimizer of all these points, of all these lines. Okay, so let's just draw the region to understand it better. So I'll just take this minus 3 first. So what I'm taking here is mu. And here I'm going to plot all these function values, each of these. Okay, so that's what is going to be on the y-axis. So, so when it is minus 3 for this function, what it's going to just look like is this. So you have a horizontal line. Okay. Now maybe let me use a different color. Okay. So now so that is the first one. So this is taken care of. I've drawn this. Now minus 3 mu. So that is going to be something which passes through the origin. So what I'm actually plotting here is y equals minus 3 mu. Okay, so I'll just write this as y. So y is minus 3 mu. So something which goes through the origin but with negative slope. So something like this. Okay. Yeah. So this is done. Now we have 5 mu minus 4. Okay, so this has positive slope of 5 and it makes an intercept of minus 4. So perhaps something like this, right? So maybe something of this form. Okay, and then you have mu minus 8. So that would be something like this. And minus 8 plus mu. So maybe the slope is something like this. It's lesser than the slope of this line because this was 5 mu. So something of this form. Okay, so this was mu minus 8, minus 4 plus mu, and minus 3 mu. So all these are taken care of. Okay, and we are looking at the min of these. So it's this line. And so, yeah, in this region, it's maybe this line. then I have this, and then I have this. So I think my drawings could be a bit bad. I think it may not give a complete picture, but the point is you can plot this and see for yourself. And the value, the dual now is just, okay, let's just try to compute. So in this region, this is the best, right? I mean, this function is going to dominate. So this is the line. So this one is phi mu minus 4. This line is mu minus 8. And then you have, this is minus 3 mu. And then you have a minus 3. Okay. So the point where these two lines intersect. So let me label these points A and B. So the point A is where phi mu minus 4 and mu minus 8 meet. So this is, both these are equal. So here mu equals minus 1, right? So yeah, clearly my diagram is, I guess, screwed up. So it would come on this side. So yeah, okay. So just try to plot it again, maybe with some softwares that you can see it better. So mu is minus 1 is this point. Okay, and so what is going to happen is theta of mu, for mu less than or equal to minus 1, the one that is lesser is phi mu minus 4. So phi mu minus 4 if mu is less than or equal to minus 1. Now in this range between A and B, so this is the point where minus 3 mu, so B is the point where minus 3 mu is equal to again phi mu minus 4, right? So what you're going to get is mu is equal to phi mu minus 3 mu. So mu is equal to what? Okay, I think
To half.
Mu is equal to half?
Yeah.
Mu is equal to half, okay. Yeah, right. So that's thing. So it is 3 mu. So what was the dominating? So sorry, it's phi mu minus 4, right? So the 3 mu is this line. So this is phi mu minus 4. Okay, did I again make some mistake here?
Ma'am, for mu less than equal to minus 1, then it would be mu minus 8. That line was lower.
Oh, okay. True. Yeah, I think that's where I messed up. So this is mu minus 8. And for mu less than or equal to half and less than or equal to minus 1, mu greater than or equal to minus 1 and less than or equal to half, you have this line phi mu minus 4. Okay, and for the rest part, mu greater than or equal to half, you have minus 3 mu. That's what dominates. Okay, so now, so this is the dual function and you want to maximize it. Okay, and what is going to happen is it gets maximized at this point. Okay, so you can see it graphically, but yeah, I urge you to go back and just check these plots once more and see if it is really the case that, this is the maximum. I mean, there might have been some mistakes when I drew the plots. Okay, so yeah.
So this is an example where you have this integer programming kind of a thing, right? So
yes.
So this is one of the examples where, even though this example is a toy example, but there could be cases where this integer program you can solve using the dual methods.
Yes.
You can get a lower bound. Yeah.
Yes, exactly. Yeah, and one thing specifically to note here is the D star. The optimum here is probably this point B. Okay, so at this point you have mu is half and it's minus 3 mu. So minus 3 by 2. Okay, and that is different from the primal. Primal was minus 3. Okay, so there is a duality gap here.
So it should have been lower, right? Something went wrong. I think it is not minus 3 by 2. Because minus 3 by 2 is bigger.
Right. I think there is a mistake here.
Yeah, in the calculation, but I think by the theory we know that D star always has to be less than P star.
Yes,
in particular, in this example, there is a duality gap.
Yes, so this is an example where there's a duality gap. So maybe, I think I would ask you all to check this computations again. We'll just come back to it maybe at the next class. I think we went over it a bit quickly. Okay, so I think we are out of time. We are much ahead of time. So what I'll do is we'll just wrap up here. So next class, I'll just tell you some sufficient conditions when strong duality holds. Okay, and then we'll just see an example of how you can use the dual to construct a primal solution as well. Okay, so yeah, so I will just stop here and I'll hang back if there are any questions. If not, we meet on Thursday at 10:30. So thanks a lot for being here.
Thank you.